So in this video, we're going to focus more on running all three different link functions in R, making sure we feel good about how the code changes and then how the output will affect how I write things out as well. So first, let's kind of just actually go to my R code and remind ourselves of when we've hit the Logit link function. So here's the code where I did this mod.fit was what we were doing when we had the Logit link function. All right. I'll scroll here instead. So when we go through this, we're going to be working with the exact same data set. So I'm still going to be using the GLM function. That's not going to change. My response variable is still going to be if it was a successful or unsuccessful place kick. I'm still going to be using distance as my explanatory variable. I'm still going to be using the same data set. Moving over here a little bit more. I'm still going to be using a family of a binomial. The reason why I'm choosing the binomial family here is because we're working with binary data. What you're going to see change when I fit the Probit or the complementary log is what I have here in parentheses at this link. So here we used a link equals Logit. And the rest of the information we had here was just again say what would I do with missing data and at what point will I let my iterations end. So if we look now at the Probit model, I'm also calling this mod.fit. It might be good to call it something else if you are scared of having it overriding what you had before as your Logit. But you'll notice the only thing difference is right here where I have that link equals Probit. So that's the only thing that's different in my code compared to what I had for my Logit model. The same is going to be true when we look at the complementary log code as well. So we're going to have the exact same code here with the only difference being this link function. So again, what that means a lot for me is I'm going to be doing a lot of copying and pasting of code once I know that it works, and just be changing that link function inside of there. Okay, now let's talk about using that output. So the code does not change much. You're probably going to get some different looking information out for this deviance and iterations. Again, that's not horribly important here for us. When I run the summary of my mod.fit, which is now based upon this Probit link function, as notice it says it there as well, here's going to be what we want to focus on. So first here with these estimates, which unfortunately don't line up the nicest here, these are going to be giving us our alpha hat and our beta hat for the Probit model. Similar to the Logit function, we're also going to get a z-value and a p-value to help me see if distance here is useful in predicting place kicks. Now again, first as a reminder, when you see that 2e to the negative 16, what that technically means you're doing is you're starting with 2 and you're going to move your decimal place 16 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So technically this is a really, really small number. Okay, so that's a very, 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 very small probability. That's why we would end up saying yes, distance is significant in predicting our probability of success. Okay, looking similarly here at the complementary log output. Again, I'm going to make sure I'm using the correct link function when I know which alpha hat and beta hat I'm talking about. But so here's our new alpha hat and beta hat values that we're going to use for the complementary log. Again, with a z and a p-value to tell me if distance is useful in predicting our probability of success. Okay, so let's first use those, as well as our original Logit link function, to just write out our 3 estimated models. So first, let's write out the one for the Logit that we already had. So for Logit, we had that the log of pi of x over 1 minus pi hat of x, that's what our Logit is, would be just 5.7818 minus 0.1145 times x, where this was our alpha hat and our beta hat when we had the Logit link function. Again, what I'm probably more interested in, though, is then rewriting this in terms of pi hat of x, which was our e to that alpha hat plus beta hat x, and beta, of course, here was negative, over the 1 plus e to the same value. All right, so that we've already had. That is nothing new. Let's now talk about the Probit, since that is new. First, going back to my output. So the values I want to use for my Probit, this is going to be my alpha hat, this 3.19-ish number, and then our beta hat is going to be this negative 0.06 number that we're going to be using. So then to write things out first in terms of that alpha plus beta hat x idea, it means that our phi of our pi hat of x is just going to be our new alpha hat, because again, notice it's different since I ran a different link function, as well as my beta hat times x. But then if I technically want to find pi hat of x, that is going to be our phi of our alpha hat plus beta hat x. And let me scroll over there. Okay, again, as a reminder of where we're getting those. In the last video, we just discussed the idea of the Probit. And so in one is in terms of when it's the alpha plus beta hat x, and the other one is when you actually want that estimated probability. Notice now I'm using alpha hats and beta hats and pi hats because it's based upon our data or our sample. So that's why they suddenly have hats now on them instead. Finally, I want to do the same thing with the complementary log. So these are going to be my 2 functions that I'm going to be writing out with my new values of alpha hat and beta hat based upon the complementary log. So this is where I say you want to be very careful of making sure you're getting the right output to go with the correct link function that you're looking at. So then for our complementary log. We would say that our natural log of the natural log of 1 minus pi hat of x is our alpha hat plus beta hat x. But then again, if I actually want to find my pi hat of x, then instead we're going to have this 1 minus e to the negative e to our same values we had over there. So kind of getting all three here relatively on the page here together. So what we're going to see, of course, here first is notice that for each of my link functions, I have different values of alpha hat and beta hat. As I discussed in the last video, we don't expect that these are the same, so do not freak out that they are different. But that's also why you want to be very careful of making sure you use the right alpha hat and beta hat for the correct link function that you have. Right, generally our ultimate goal though is going to be to find pi hat of x. But so notice that we're modeling them in different ways, which is why we're then getting different looking estimates of our values. We could then use these link functions to help us find some estimated probabilities. So we are going to do this when x is 20 and when x is 50. So we're going to have our Logit, our Probit, and our complementary Cloglog. And we're going to plug in an x equals 20. And we'll plug in x equals 50. Now notice I could technically plug 20 and 50 in either to this value or to these equations. Of course, I'm going to get different values, so I want to be careful. Which one do I really care about? I'm really going to want to plug it into these values because this gives me that estimated probability of success. So just be a little bit more specific down here so that we know what I'm actually doing. I'm going to find the pi hat of x equals 20, and I'm going to find the pi hat of x equals 50, just so you know which equation I'm plugging them into. So first I'm going to plug x equals 20 into this equation, which we've done before, as well as x equals 50. So we did this for the Logit function before already. But let me just go ahead and write those numbers down as well. So we got a little bit more than a 97% chance of making the 20-yard place kick at a yard distance of 20 with a Logit function. And for a distance of 50, it was still actually a little bit more than a 50% chance of making the kick using the Logit link function. Now let's do the Probit. So the first thing I want to do is plug in 20 for my x here. I suggest trying to kind of work this one here with me as well. All right, so first, when we plug in 20 for x, we should get a value of about 1.943. So just kind of doing a little bit more work here. I technically want to find then this phi of 1.943. So what that is telling me then is I want to go to my normal table and find 1.943. Now notice I only have 2 decimals here in my z table. If I actually use r to calculate this probability, it's going to be much more accurate since it's not going to be limited to 2 decimal places. But so if I use about 1.94, I would find then my probability is going to be 0.9738. So then that's going to be my estimated probability of success using the Probit model. Now we want to do the same thing where x equals to 50 instead. So let's plug in 50 into our equation. and we would get about 0.0645. Using our limited table here, I can only look up about 0.06 instead, which would give me about 0.5239 using my table here. Okay, so for that one I did actually have to use the table. We'll also show how to get those values from R, which will be a little bit more accurate than us doing them here by hand. Finally, for the complementary log, going up here, I'm going to plug in 20 into this equation and then 50 into this equation. Make sure you feel comfortable in doing those yourself by hand here. So just making sure you're getting your order of operations correct as well. So when I do that for x equals 20, I should get about 0.97736. And when I plug in x equals 50, I get about 0.54582. So you'll notice we do get different probabilities at x equals 20. They're much more similar than they are at x equals 50. So there's a little bit more differences there for the x equals 50 value. So that's using the equation to come up with some probabilities. Now we can also use R to get us these probabilities as well. And so let's look at where I've actually already done this in our code. Get rid of that real quick. All right, so in our Probit code here, so it does start at the top of the next page. So what I'm doing is I'm actually going to find my values here for the Probit. Here I'm currently using the Probit alpha and beta hat. So the first thing I'm doing is getting this thing called lin.pred. What this lin.pred is going to be doing every time I actually use this terminology, it's just going to be do that alpha hat plus beta hat times x. So just getting something like linear predictor, that's just what I mean by that part. So then in order to do that, I need to get my alpha hat and my beta hat. Where I'm getting those is from where I fit my model to begin with. So my most recent run here of my mod.fit is with the Probit. So that $ coefficient 1, again, just pulls off the first value here, and then the second one will be the beta hat here. So that's what I'm doing there. Then I'm going to take that value, that alpha hat plus beta hat x, and find it in that p-norm function. What I want to find is of that linear predictor, comparing that to what we did. So what that lin.pred is hopefully going to give me is, scrolling, this 1.943 for that first value when I run it. So let's actually go ahead and run our Probit code. Just so you can kind of see it. So see this lin.pred is numeric and it's about 1.94. We had 1.943. And then if I do the p-norm of that, it's going to now give me that estimated probability of 0.973992, which is a little bit different than what we found when we did it by hand because we were limited by our table. So kind of like from R, we would get 0.973992. And then we can do the same thing for x equals 50. So that's all I'm doing here is changing this to 50. So I copied and pasted that same code. Now our lin.pred is that 0.06-ish number that we found as well. And finding that p-norm of it gives me a little bit different than what we found from our limited table of 0.522556. 5, 5, 6. So a little bit different there. Then we can do the same thing with our complementary log function as well. So again, here's the output I'm going to start looking at. So assuming I've run this function, here's my new alpha hat and beta hat. I'm doing the same idea down here. It's first I'm going to find that lin.pred. So again, that's just doing the alpha hat plus beta hat times x. But then to actually get my alpha hat that I want, we're taking 1 minus e to the negative e to that value that we just found. So that's exactly what I'm typing up here. So I want 1 minus e to that negative e to this value I just found. And when I run that code, I get 0.9773586. Which is really close to what we found here. And then I can do the exact same thing. Oops. Changing my distance from 20 to 50, which continue on the top of the next page here. Sorry for all my scrolling. Giving me about 0.5458166. So pretty close to what we found when we did it by hand as well. So I can use R to help me find those predicted values. Finally, let me talk about some of the extra code that you see here. And this is going to be useful for me later when I actually want to get a plot of all my different link functions. So if notice for here, for example, for the Probit, I did it for the 20 yards and 50 yards. But I could do this for any yardage that I really want that makes sense to plug into my data. So I'm going to do it for every distance between 18 and 66. So that's what I'm doing here. Notice that I'm using the same idea of the code that you see up here, except for instead of multiplying by 20, I'm multiplying by a sequence from 18 to 66. And I'm going to go by ones. So it's going to go 18, 19, 20, etc., all the way up to 66. So it's going to allow me to do all of those at the exact same time, so I don't have to do them one by one. Then now that I have this long list of those, I can find the p-norm of each of those values. So that's just all I'm doing here. So let's actually run that code here in R as well. So now if I look up this Probit pi hat, you'll see it's full of all these different numbers. So this is for 18 yards, 19 yards, 20. So you can see there's our 20-yard estimated probability of success. So now it has all of the values in there for distances of 18 to 66. Then I'm just going to be doing the same thing for my complementary log. So same idea, I'm using the same sequence from 18 to 66 by 1, but then making sure I use my correct function for the complementary log. Now, one question we already might have is which model is best? So let's go ahead and talk about a few of the things that we could already look at to understand which link function might be the best one to use. So first off, it's not the most easy question to really answer. There's not always like this is what you should do. So here might be some things that we would know. So for example, sometimes we might know the transformation is normal. If that was the case, the Probit would be the way to go since it knows we have that normal distribution there. We could fit all three on a graph of the data. to see which fits the best. And I put fits, of course, in quotes, is how do you exactly tell which one fits the best is a little bit harder to do. Another criteria that we could use is we could use this thing called Akiaki's information criteria, or is labeled as AIC. When I would look at that number here in R, lower is considered better for the AIC. So those are different ways I could make a decision of which link function to use. The one that gets used most often when there really doesn't feel like there is a best is we have a tendency to use the Logit as sort of the safe one. And the reason why people tend to use the Logit as sort of the default or the safe one is simply because of its interpretations. It has really nice interpretations. And the reason why it has nice interpretations, if we think that we're doing this log of pi over 1 minus pi, which is the log odds. And so since it naturally has this odds showing up in it, it makes it very nice for interpretation sakes. So we will continue this discussion in the next video to try to figure out which of our models is the best one to use for this data set. But we're also going to talk about using R to help us create new ways of predicting, more specifically how we can have intervals on those predictions as well.